Okay, this is lesson 3.1b, characteristics of polynomial functions. Last time we looked at the actual graphs and the equations and what they had in common. Now we're going to look at just the equation, and we're going to see what we can find out from the graph and sketch a general graph from the information. So again, you'll notice they are the identical equations, but that's okay. So we're going to take a look, and when we get this information, our linears. What do we know about linear equations? What do we know about their degree and the turning points from last time? What is the degree?
Oh, the degree is the highest exponent of the variable.
You're exactly right. And the turning points. How do we know how many turning points an equation is going to have? How do we know? Pardon? One less than the degree. So, constants always have a degree of what? What do we know? They have a degree 0 because they are 0 variables, 0 exponents on their variables. So that's why it's 0 degree. Okay? You need to have a variable to have a degree. This guy, linear, is degree 1. They have x exponent 1 everywhere. X exponent 1. Okay? So that's degree 1. So degree 1, we know a few things. So these guys are degree 1, linears. So if they're degree 1, there is no change of direction. That's what we know already. Okay, there's no change of direction. We also know that the C value is what? What location is the C value on the graph? What do we know about that?
Y.
It so is. It's the Y-intercept. Okay, so we know those things about linear functions. So before we even go to our calculator and graph these, which we've already graphed, we need to just identify characteristics about them. So, linear, degree 1, they have no change of direction. The C value is always the Y-intercept. They're either going to increase or they're going to decrease, because your X will either be positive or negative. And again, that's what's going to tell us if it goes up or down. So, positive is up, negative is down. Okay, and that means the variable of x. So, if the variable is positive, the graph will go up. It'll increase. If the variable is negative, it will go down. So, for example, if I've got y equals negative 2x plus 4, negative 2 tells us that it's going to go down. Okay, that's what the negative sign tells us. It's a decreasing graph. The 4 tells us where he's going to be on the Y-intercept. So, when we graph linear equations, we always start with the Y-intercept. So we know this guy starts at positive 4, way up here. Okay? Then we do what our slope is supposed to do. Now, the slope is always the digit in front of x. He's going to tell you how he's going to move his dot. Where is he going to go? Well, we know it's going down. The negative sign will always go to the top number if it's a fraction. So, for example, I could have y equals negative 3x over 4 plus 9. So I could have an equation that starts at positive 9. That's what this tells me. And then my slope is in front of my x. This is going to tell me how the dot's moving. Now, my dot that starts at positive 9, I'm just going to erase the information here. Hopefully you've got it written down, because it's going to go bye-bye. Okay. So, this next example that I'm doing, we've got a positive 9. So I'm going to make my first dot on positive 9. That's where we always start our equations. Now, the bottom number of our slope, the bottom number always moves to the right. The top number, because it's negative, is going to go down that many steps. Now, if it was a positive, it would go up. So now, my slope is going to go 4 to the right, 3 down, 4 to the right, 3 down, 4 to the right, 3 down. So I would go 4 to the right, 3 down, 4 to the right, 3 down. Okay, and then I would continue. And that's where I make my dots. And that's how I know where to connect them to create my linear equation. Okay? So, linear equations again. What do we know just from the equation? our y-intercept, and how the dot has moved for our graph.
So if the score down the bottom is negative, which would never be because it's a fraction, it would move to the left.
No, unfortunately, the bottom number will always move right because the negative sign, as you mentioned, wouldn't end up on the bottom. The negative would float to the top. If it was not a fraction, so we could have y equals, let's say, negative 2x minus 6. Well, if we had something like that, we need to create a fraction for our x, so he'd be over 1. The bottom number will always move to the right. Okay, so he's got to move right. So this guy here would start at negative 6, and he'd go 1 right, 2 down, 1 right, 2 down, 1 right, 2 down. So I'd start at negative 6, 1 right, 2 down, 1 right, 2 down, and I'd make my dots. And that's how I would create my line there. Okay? So these are our linear equations. This is exactly what we know just from looking at the equation. Okay? Now we're going to go to quadratics. We're going to figure out what do we know from a quadratic just by looking at its equation. So, a couple things. Quadratic always has to have an x squared as its largest exponent. That means this guy is going to be a degree 2. And we know degree 2's change direction. How many times? Once only. So, there's one turn point. So if there's a turning point, that means the range has a boundary. So one turn point, so the range has a restriction. The x value does not. Okay? The domain does not have a restriction, only the range because of the turn point. So basically, it's like kicking a football. If you kick that football, it would go up, 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 and then it would eventually turn around and fall back to the earth, right? And hit the ground. Same thing as if you're going to launch a rocket. You launch something into the air, you know, according to gravity and Newton's laws, it's going to turn around and come back down and hit the ground. Okay? So, we know that it's going to change directions. So because of that, we know a couple things again. The c value is the same as with our linears. The c value, again, is still the y-intercept. So we do know that. We also know a couple more things about degree 2. So if I look at a degree 2 equation, it's going to tell me how many times it can touch the x-axis, the maximum amount. And the maximum amount of times it can touch the x-axis is equal to its degree. So that means a degree 2 is going to touch the x-axis maximum twice. But we already know that with quadratics, sometimes they don't touch at all, and sometimes they only touch once. The degree tells us how many times they can maximum touch x. So if we go down to a cubic in a few moments, if it's going to be a degree 3, they can maximum only touch x 3 times. Okay? But again, sometimes they won't. We have different forms. So, for these guys, our degree 2 in our equation, so the maximum number of x-intercepts is equal to the degree. And that's what we know already just by looking at the actual equation. So, the maximum number of intercepts is equal to its degree. Okay? So, I'm just going to sketch a couple. So, we've got some that never touch. So they will be above the x-axis or below, doesn't matter where, they could be anywhere. We've got some that touch only once, and then they change directions and go back down. We've got some that will touch it twice. Okay, now whether it's up or down, it doesn't matter. So that's how many times it can touch. But again, the degree is equal to the maximum number of times it can touch. Okay. We're going to do the exact same thing when we analyze a cubic equation. And again, we haven't taken our calculator out. We have not graphed any of these. This is just taking information, what we know from an equation. Okay? All right. I'll give you a sec to finish writing that down. Okay, let's move on. Moving up to the cubics here. So cubic functions. We know a couple things about our cubic functions. So cubic functions, again, are going to be x cubed, so it's degree 3. So the maximum number of turning points is how many? How many times can it change direction for a cubic? 2. Okay, it's going to be always 1 less than the degree. So the maximum number it can change directions is twice. Now, we've also got a special situation. We've got a point of inflection. And this is a flat spot on the graph. And this is where it does not change directions. So it does not change directions. Okay? So, an example of that would be if I take an increasing function, I go up, 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 and then I go a flat spot, and then I continue to go up. This would be considered my flat spot. That is my point of inflection. So, it's not showing that it dropped below, okay? It's just continuing increasing. We can also have some that go down and do the same thing. So we can have a down graph that does the exact same thing, and you'll have a flat spot. So, sometimes your flat spots look like diagonals, and that's totally okay. But they will not change direction. That's comparative to the other types we've got. We've got ones that will touch 3 times. So this guy will touch the x-axis 3 times. And we've got some that touch it only twice. They're going to touch right there and touch right there. So there's a number of different types that you're going to see. Okay? But again, what do we know just from the equation? Well, because it's a degree 3, we know the domain and range are going to match degree 1. So, degree 1 and 3 have the same domain and range. Okay, same domain and range. Now, because of our spots and us changing directions more than once, we've got spots on our graph that we now call a relative maximum and a relative minimum because our graph changes directions. So when we've got a quadratic, if I were to show you a quadratic, I'll just draw a teeny one here, it will change directions once. So you're only going to have a minimum point, and there's only one of them, one minimum point. However, with a cubic, he changes directions twice. So you're going to have a maximum and a minimum in almost every cubic function. Here we have a min, over here we have our max. So, because we've got a maximum and a minimum in each function, we call them relative max and mins. Okay? Okay, I'm going to give you a couple minutes to write that down, and then we're going to move on. Okay, again we are referring back to our general form. General form is where we always have an a in front of our first variable. So if it is a quadratic function, we're going to have 3 terms. Okay, quadratic typically is going to be 1, 2, or 3 terms. Okay, so you could have x squared by itself, right? So cubic will have 1, 2, 3, or 4 terms. If it has 4 terms, that means it changes directions multiple times, and it's got a y-intercept, very specific. Okay, every single one of these will have a y-intercept always. And again, for a linear function, we have a in front of x, x to the 1. Leading coefficient, we've discussed this before. The leading coefficient is the digit in front of the variable with the largest exponent. So in this case, for each of these general forms, for the linear, quads, and cubics, it would be the A value. Your A value would be your leading coefficient. Okay? All right. We're going to talk about, I'm going to give you some time, and you're going to go through these, and I'm going to give you very specific equations, and I'd like you to fill out the chart and analyze what's going on with the questions, okay? So, the similarities and differences we're going to look at. So, here we go. Here are the questions I'd like to look at. So, y equals negative 3x plus 7. Okay, that's your linear function to analyze. The quadratic, y equals 2x squared minus 4x minus 9. And the cubic function, I'll put down here, y equals negative 4x cubed minus 2x squared plus 3x plus 2. Okay? Actually, we're going to go plus 5 on the end. We'll go plus 5. So I'm going to give you a few minutes. I'd like you to please go through all of these. You shouldn't have to graph them. You should be able to find out almost everything from this. Okay? So I'll give you a couple minutes. Push pause now and when you're ready. Okay, a few features of our linears and cubics we're going to go through. We're going to talk about end behaviors. So we have an increasing function or decreasing functions. So an increasing function for a linear, doesn't matter where you put it. Same thing for decreasing, doesn't matter where you put it. Let's locate our quadrants. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. So I'm now going to draw some cubics in. We're going to do an increase and a decrease. So when I take a look at my end behaviors, that's talking about the tails and which ends they point. Where does the graph start? Where does it end? We graph things according to left to right, the same way we would read a book. So if I look at the end behavior for a linear, for an increase, it's going from 3 to 1. That means quadrant 3 all the way up to quadrant 1. If I look at my cubics, it's also going 3 to 1 for an increase. These will always match, 3 to 1, 3 to 1. Going over to the decrease, these will also match. Decrease, quadrant 2 to 4. Down here, same thing, quadrant 2 to 4. It will be a tad different when we talk about quadratics. So, these ones will match because they have an odd degree. Degree 1, and this guy's a degree 3. So degree 1 and degree 3 have very similar characteristics. Their domains and their ranges will also match. Domain being XER and range being YER. They will always match. Moving on to a few quadratics. Increase and decrease. If I have an increasing function, it's pointing upwards. If I have a decreasing function, it's pointing downwards. Again, we're going to label our quadrants. 1, 2, 3, 4. 1, 2, 3, 4. So, an increase is always going to go 2 to 1. A decrease is always going to go 3 to 4. So, they're either going to start on the top of your graph and end on the top, or they're going to start at the bottom and end at the bottom. And that is common for even number degrees. Even degree functions. So if we had a degree 4, degree 6, degree 8, they would have these similar features. Okay? Now, domain and range. Domain will always be XER unless we're specifically problem solving. Range is always going to have a boundary because we have either a minimum or we have a maximum, which is a change of direction. That means we will have a boundary on the range. Let's take a look back at the chart. You should have finished your chart. Let's take a look at what you've got done. So follow along. Here we go. Linears and behavior. Well, I gave you a decreasing one. The question that you had to do was y equals negative 3x plus 7. So the end behavior for this guy going down is going to be a 2 to 4. He is a degree 1 because he has an x exponent 1. That's our degree. The number of turning points is always 1 less than the degree, so it's degree minus 1. So in this case, it's 0. Our constant term is positive 7, which is identical to our y-intercept. These are identical, always. As I mentioned, there's a word missing, number of possible x-intercepts. Well, for degree 1, this is going to be equal to the degree. Okay, so the number of possible x-intercepts is always equal to the degree. So degree 1 will have 1. Now, leading coefficient. This is always the a value of your equation. So in this case, my leading coefficient is a negative 3. Let's take a look at the quadratic and make sure you've got the same thing written down. Y equals x squared minus 4x. 2x squared, pardon me, minus 4x. Minus 9, thank you. So the end behavior, the x squared is positive. That means it's going up. If he is an up function, he is going 2 to 1. My degree matches the highest exponent on my x variable, which is 2. My turning point is 1 less than the degree, so that's going to be 1 turning point. My constant is a negative 9, which is identical to my y-intercept. The number of possible x-intercepts equal to my degree, 2. And my leading coefficient is what is in front of my x squared, and that is going to be a 2. Well, let's take a look at the cubic function. So continuing with our cubic function says y equals negative 4x cubed minus 2x squared plus 3x plus 5. Okay, so this cubic, again, if we take a look, end behavior, we have a negative sign. The negative means he's going down. So our down cubic is going to go 2 to 4. Same as our linear, you'll notice that is also decreasing. Degree, this guy is a degree 3. Turning points is 1 less than our degree, so that is a 2. Now we want to have our y-intercept. Our y-intercept is the constant, the one without the variable, so it's going to be a 5. So our constant is 5, which is equal to our y-intercept. These will always be equal. They are identical. Number of possible x-intercepts equal to the degree, so 3 possible. Coefficient, our leading coefficients in front of our x cubed is a negative 4. Check your work. Make sure it matches. Okay, well, let's move on to the next section. Okay, so we have a few questions to answer. The first one says, what is the relationship between the sign of your leading coefficient and the end behavior? So the sign, being positive or negative, determines where your graph will start and end. Okay, so it determines the end behavior. Okay, it determines the end behavior. Because positive is going to go 3 to 1, negative will go 2 to 4. Again, it's a degree 1 or degree 3. The constant term and the position of the graph. So position of the graph. What do we know about our constant term? He is the y-intercept. Thank you. Is the y-intercept. So if it's the y-intercept, it tells you where you're locating your graph. Has the graph moved up and down from 0? Basically is what it's showing you. All right, if you can see at the very bottom here, we got number 6. It says, what is the relationship between the min and max number of X-intercepts with the degree? So if you look on your chart, what do we say about the degree and the maximum number of intercepts? It's the same. Good. They will be the same. Okay? So, degree 3, maximum number of intercepts will be 3. Degree 2, maximum intercepts will be 2. Degree 1 is 1. What would a degree 0 be? That's just a y equals a digit. That's just a linear function. It's a constant, right? There's no variable. Let's take a look at the other couple questions that we've got to answer. Question 7. How can you predict some of the characteristics of a cubic from the standard form? Standard should say general. It should say general form. Now, a couple things we found out about this. We found that depending on the number of terms, because a cubic can have 1, 2, 3, or 4 terms. So that means you've got 4 different situations of cubics. So if it's got 1 term only, that's going to be your point of inflection. That's not going to change directions. 2, 3, and 4, that's just going to change directions, and it's going to change where your y-intercepts are. So that means you're comparing equations like this. Y equals x cubed. Y equals x cubed. Oops, pardon me. That's 2. X cubed plus 2x squared. 3 terms could be y equals x cubed plus 3x plus 1. You don't always have to have a squared term. So this guy could have had an x squared and no constant. So there's multiple different ways. We could have 4 terms where we're going to have a cubed, a squared, a degree 1, and a constant. So each one of those are going to tell you what kind of graph you're going to see. Are you going to see a graph that is a point of inflection? Point of inflection meaning it's not changing directions. That's when you've only got 1 term. Okay? These guys that have no constant, when I look at this guy with no constant, and I look at the first one with no constant, these ones are going to go right through 0, 0, the middle of the graph. They have to, because there's no y-intercept other than 0 located here. Okay? So that's what they're talking about. So this is one for you to practice on. Here is a cubic function. It says, do not graph it in your calculator. Determine what you know about it from the equation only. Okay? I'll give you a couple moments to do that. Push pause now and play when you're ready. Okay, let's see what you guys got. So, we're not going to look at anything from the calculator. We see it is a degree 3. So degree 3, possible intercepts is identical to the degree 3. The y-intercept is the constant. Okay, the guy without the variable, so he's going to be positive 1. End behavior, because he's going down, is going to be 2 to 4. Domain and range, XER, YER. Those are standard for degree 3 and degree 1, even odd degrees. Number of possible turning points, that's your degree minus 1. So 2. It's going to change directions twice. So hopefully your chart's pretty good. Now, which one's it going to look like? We try to match our graph at the bottom. We have to match a chord. The first thing you look at is you look at the up or down. So the negative right here tells me it's going down. So the up graphs, B and D, are not possible answers. How do I know they're going up? Because you're reading the graph from left to right. These guys start in the bottom and they go up. Okay? If we look at these guys, they start at the top and then go down. That's why these ones are decreasing. Now you have to take a look at the y-intercept. So first of all, you find increase, decrease, then you look at the y-intercept. This guy's got a y-intercept of 1. If we look at the y-intercepts, this guy's showing a y-intercept of negative 1. This one's showing a y-intercept of positive 1. So that means we only have a possible answer of C. okay? Because it's going down and a positive y-intercept, okay? All right, check your work. Okay, we're now going to take a look at two equations. One is a linear and one is a quadratic. You are also going to do both of those. Now, I'm going to let you do those in a moment. I want to focus right now on the bottom one. We're going to try and identify the type of graph we can get from this bottom. So let's take a look here. We're giving us boundaries. If I have a boundary on my range, what does that tell me about my degree automatically? You betcha. So this tells me I have an even degree. So that means it's not degree. Oh boy, I can't spell today. Degree. Okay, so even degree. So it's got to be x squared. We don't deal with x to the 4. So we know it's got to be an x squared graph. Then it says it's got a y-intercept of positive 4. So I know it's got to touch through positive 4. So I'm going to make my dots. But it tells me my range boundary. Am I allowed to go below negative 2? No. It tells me when it points to the right, that means above. So that means I need to be above negative 2. So that's my boundary right there. So that means I could have any degree 2 quadratic that could be going, it must go up. Why is it not allowed to be a down graph? Because it can't go below. Down graphs will go from 3 to 4 when they do this. It must be an up graph because I can't go below negative 2. So that means I've got to have a graph that's going to come low, touch, and then go through positive 4. So I could have a graph that looks like that. I could move it over anywhere I want. I could make it as narrow as I want. I could make it as wide as I want. I could go through here, touch, and go back up. Okay, so you could have a wide graph.
Doesn't even have to touch, doesn't it? It says greater than or.
Right, greater than or equal. You're exactly right. So it doesn't even have to come this low. We could have one that is way up top here, and maybe he's just going to touch negative 4. That's okay. Okay? So, because they did give us a specific boundary, though, they're telling us it is going to sit on that line, because they did give us a specific boundary. If they gave us a range of positive 4, that means my y-intercept and the range would be the same. Okay? But it didn't. So this graph actually up here, yes, it's possible, but they did give us the boundary of here. So they are going to come down and touch there for a vertex. Okay? All right. You've got a couple minutes. Please fill out the chart at the top, and we will take that up in a moment. Okay, fill the chart. Okay, we've got a couple minutes. Let's take a look and make sure you've got the right information. So we've got linear. This is degree 1. Here we've got degree 2. So degree 1, possible number of x-intercepts is 1. Degree 2, 2 possible. Y-intercept is always our constant. So in this case we have a negative 5. In this case we have a positive 8. End behavior, this is an up graph, so it's going to go 3 to 1. Now this guy here is a down graph because x squared is down, so this one's going to go 3 to 4. Domain, XER for both. Range for degree 1 is YER. And possible number of turning points is 1 less the degree. It's degree minus 1. So here we have 0. Here we have 1. We're going to go back to range of a quadratic. Range of a quadratic has a boundary. So because it has a boundary, we need to find the vertex. So your vertex is the max or min point. So we're going to grab our handy-dandy calculator. This is the only thing you need your calculator for. You're going to turn your calculator on. I just need to clear the ink layer. Has everybody got that written down so I can turn the calculator on? Okay. So here comes the calculator. So you're going to turn your calculator on. In your y equals, you're going to input the equation. After you've input the equation, you're going to hit graph. Now, by the way the graph is shaped, if it looks like a hill or a mountain, it's going to be a maximum point, a maximum height. If it looks like a U, then it's going to be a minimum point. We've got a maximum point. So in order to find that maximum point, that's our vertex. Okay? So we need to hit second trace. Everything's in our second trace menu. We're going to find number 4, the maximum. So we hit number 4. Now, our cursor we have to move with our left and right arrows. We need to move our cursor to the left because it's going to say left boundary, right boundary. You always need to be to the left of the highest point. You hit enter. Then you move your cursor to the right of the highest point and hit enter twice. That gives you your maximum point. So here our maximum point is at -1, +10. So I am now going to go to my information here. So I got a vertex of -1, +10. My range uses the Y value. Okay? So the range uses the Y value of the max or min point. Okay, of the vertex. So, because it's a down graph, we have to point, we're going to do this. I'm just going to write above, our range is going to be here. Y, now we're going to point like this. Left because it is a down graph. Left of our max point. So now I'm going to write 10. This is my complete range. Okay? And again, it comes from my max or min point. And again, it's the Y value of the max or min point. Okay? That's the number we're putting in there. So, because it was a down graph, our arrow had to point down. It had to point left, lower. So, if it was an up graph, for example, if I have one pointing upwards, our range would start as greater than or equal to our minimum point, because this would be a minimum point here. Okay? So that's how the range of a quadratic works. And everything is in your second trace menu, okay, under max or min. Okay, and that's how we find our vertex. And our vertex, again, tells us our max point, but it tells us where we can chop our graph in half, where we can fold it, and it'll be a mirror image on itself. Okay? That's our axis of symmetry that does that. That's just the X number. Okay? The Y number is how high or how low it goes. Okay, this concludes lesson 3.1b, analyzing equations of polynomials.